In the previous lecture, we calculated, or we derived an expression for the heat exchanged by radiation between two infinite parallel plates, which are maintained at different temperatures T1 and T2. We got an expression for the heat exchange rate, and today we want to do a similar derivation, but we would like to calculate the heat exchanged by radiation now in the annular space between two infinitely long concentric tubes. So, once again it is a two surface enclosure. The outer surface of the inner tube is one surface, the inner surface of the outer tube is the other surface. These two surfaces make up a two surface enclosure. Looking at the sketch, the outer surface of the inner tube is this one here, and it is maintained at a temperature T1. It is maintained at a temperature T1. The inner surface of the outer tube is this surface, and it is maintained at a temperature T2. The outer surface of the inner tube has a radius R1, and the inner surface of the outer tube has a radius R2, and the space, the annular space, is the radial distance between R2 and R1. That is the annular space in which the heat exchange by radiation takes place. Let us assume, as in the previous case, that the surfaces are diffuse gray. Let us assume that the surfaces are diffuse gray and that the emissivities are epsilon 1 and epsilon 2, as in the previous case. And since Kirchhoff's law will hold true, it follows that the absorptivities are also epsilon 1 and epsilon 2. Also, we will assume that the surfaces are opaque, therefore, the reflectivities are 1 minus epsilon 1 and 1 minus epsilon 2 respectively. All right. As in the previous case, we will make the same assumption. So, the only difference really is that we have a situation now in which we have changed the geometry of the situation now. That is the only change really that we have got. So, with this geometry, we would like to know what is Q1 and what is Q2. Q1 is the rate at which heat is supplied, let us say per unit length, supplied per unit length from the surface 1 or per meter length. Q2, the rate at which heat is supplied per meter length at the surface 2. If T1 is, let us say, greater than T2, it follows that Q1 will be a positive number, Q2 will be a negative number, and Q1 will be equal to minus Q2 as in the previous case. If T1 is less than T2, the situation will be reversed. Now, again we are going to consider radiation emitted by one surface and which goes back and forth in the annular space and is successively absorbed and reflected at the surface which it encounters. That is how we are going to proceed. Once we get terms for these quantities, we will, like in the previous case, generate a geometric progression and sum it up. So, let us proceed. Let me draw a sketch of the two tubes and the annular space in an end elevation, so that I can show the rays going back and forth. Let us say that this is, the radius R1 and this is the radius R2. All right. And this is the annular space in which the heat exchange by radiation is taking place between the surface 1 and the surface 2. Consider now the radiation emitted from some element on the surface 1. Let us say I have some element on the surface 1 and let us say we consider radiation emitted from it. The emissive power of surface 1 is E1. So, let us say symbolically that E1 is what is emitted, E1 so many watts per meter squared is what is emitted from this surface. E1 will be given by epsilon 1 sigma T1 to the power of 4 by the Stefan-Boltzmann law. All right. Now, this arrow is symbolic, mind you, radiation from this elementary surface is really going off in all directions. So, the arrow is simply symbolic, showing radiation is being emitted from here, and ultimately all of it has to reach the surface 2. Mind you, this is a case in which the surface 2 completely surrounds the surface 1. Therefore, F1 to 2 is going to be 1. All the radiation from any element on 1 has to reach 2. All right. So, F1 to 2 is 1, and also the reciprocal relation tells us that F2 to 1 is going to be A1 upon A2, which is nothing but R1 upon R2, because we have two infinitely long concentric tubes. All right. So, this is a situation in which F1 to 2 is equal to 1 and F2 to 1 is equal to A1 by A2, which is nothing but R1 upon R2, rather 2 pi R1 L upon 2 pi R2 L. The 2 pi L will cancel out. So, I will get R1 upon R2. So, now let us go back. Let us consider the radiation emitted from this element. E1 watts per meter squared are emitted. When all this radiation emitted in all directions of a hemisphere reaches the surface 2, the amount that is absorbed here will be epsilon 2 E1. So many watts per meter squared will be absorbed, and a certain amount will be reflected, all right, which will again be reflected in all directions like this. Out of this reflected amount will be 1 minus epsilon 2 into E1. Out of this reflected amount, a certain amount will go back to the surface 1 and a certain amount will go back straight to the surface 2, because the F2 to 1 is A1 upon A2. So, what is the amount that goes directly to the surface 2 itself from 2? Well, the amount that goes to surface 2 directly will be the amount that goes to surface 2 directly. Let me draw it in this point here rather than that arrow, just let me show it here. The amount that goes to surface 2 directly will be 1 minus, this quantity is going to be 1 minus A1 upon A2 multiplied by 1 minus epsilon 2 E1. All right. That is the quantity that is going to be, because the amount that is absorbed is epsilon 2 E1. So, the amount that is reflected is 1 minus epsilon 2 E1, and out of that the amount that goes directly to surface 2 will be 1 minus A1 by A2 into 1 minus epsilon 2 E1. The rest goes back to surface 1. What is the quantity going to surface 1? Well, let me show it by an arrow. The quantity that is going to surface 1 is the difference. So, that is going to be, let me show that here. The quantity going to the surface 1 itself will be A1 upon A2 into 1 minus epsilon 2 into E1. Okay. That is the quantity that goes to the surface 1. Out of that, the quantity that is going to be absorbed in the surface 1 will be, the quantity that is absorbed in the surface 1 will be that multiplied by epsilon 1, and the quantity that is reflected back to surface 2 will be the difference. So, it will be 1 minus epsilon 1 multiplied by A1 upon A2 multiplied by 1 minus epsilon 2 into E1, and out of that the quantity that is absorbed will be this quantity which I have put down here multiplied by epsilon 2. So, if I multiply this quantity which I have got here, I will call this as 1, I will use this as Roman 1, and I will call this as Roman 2. Okay. What is here Roman 1 is the quantity that is coming to the surface 2 and after reflection from surface 1, and this expression is the one that is coming directly to surface 2. All right. If I multiply both of these by epsilon 2, that is the absorptivity of surface 2, I will get this quantity which is finally absorbed at the surface 2. So, I am going to get the arrow, the big arrow showing the amount absorbed will be epsilon 2 in the bracket 1 plus 2. All right. That is what is going to be the quantity. And if I work that out, if I work out that expression, I am going to get epsilon 2. If I work out that expression, I am going to get epsilon 2 into 1 minus epsilon 1 A1 upon A2 multiplied by 1 minus epsilon 2 multiplied by E1. Let me just check again, 1 minus epsilon 2 E1, that is here, and if I multiply this I will get 1 minus epsilon 1 epsilon 2. And the whole thing is to be multiplied by epsilon 2. Am I right? Just let me check that. Yeah, that is okay. So, this is the expression I will get for the quantity that will come back to surface 2 and absorbed by the surface 2. Now, this is the first set of absorptions and reflections. I can go on doing this and generate terms like this one, all right, and therefore, I can say, having done this, I can say the following. I can say rate at which radiation emitted by inner tube 1 and absorbed by outer tube 2 is equal to, I am going to take them term by term now. I take A1 E1 outside because that is common, all right. I will take A1 E1 outside. A1 is the area of the surface 1 and E1 is the emissive power. So, I am going to take that outside and I will get the terms inside to be, the first term is epsilon 2, the next term will be 1 minus epsilon 1 A1 upon A2 multiplied by 1 minus epsilon 2, okay, multiplied of course by epsilon 2, plus the next term is going to be, which we have not derived, but you can do on your own, 1 minus epsilon 1 A1 by A2 the whole squared 1 minus epsilon 2 the whole squared multiplied by epsilon 2 plus so on. That is what we are going to get. So, we derived the first two terms, mind you. The first term was A1 E1 epsilon 2. Let me go back to the sketch. The first term which we derived was this one. A1 we did not write down, that was the area of the inner tube, into epsilon 2 E1, that was the first term. And the second term we derived was this one, for what is absorbed by the surface 2, that is epsilon 2 into 1 minus epsilon 1 A1 A2 into 1 minus epsilon 2 E1, that was the second term. All right. This is now very easy to sum up. We can take epsilon 2 also outside. So, we get A1 E1 epsilon 2, and inside the bracket we will get a geometric progression, and if you sum up that geometric progression you will get 1 upon, it is a very simple geometric progression, 1 upon 1 minus epsilon 1 A1 by A2 into 1 minus epsilon 2. That is the summation of the geometric progression, the infinite series that we have. And if we clean up this expression a little, we will get, this is further equal to A1 E1 epsilon 2 divided by epsilon 1 A1 by A2 plus epsilon 2 minus epsilon 1 epsilon 2 A1 over A2. That is what we will get. Okay. This you can do on your own, the summing up of the geometric progression. So, that is the expression we will get. This is the rate at which radiation emitted by the inner tube is absorbed by the outer tube. Now, in exactly the same way, do the reverse calculation. Calculate the rate at which radiation emitted by the outer tube is absorbed by the inner tube. Similarly, I am not going to derive this now, I am saying similarly, rate at which radiation emitted by the outer tube by the outer tube 2 is absorbed by the inner tube 1 by the inner tube 1 equals, now this derivation I am not doing, it will come out to be A1 epsilon 1 E2 divided by, if one does the derivation, you will get the following, and I would like you to do this on your own as an exercise, multiplied by epsilon 1 A1 over A2 plus epsilon 2 minus epsilon 1 epsilon 2 A1 over A2. All right, that is what you will get. Therefore, now the Q1 to 2, that is the heat exchange between the two surfaces 1 and 2, the net heat exchange between the two surfaces 1 and 2 is given by, therefore, Q1 to 2 is equal to A1, the difference of the two. So, we will say A1 into bracket epsilon 2 E1 minus epsilon 1 E2, the difference of the two terms, divided by epsilon 1 A1 upon A2 plus epsilon 2 minus epsilon 1 epsilon 2 A1 upon A2. That is the net heat exchanged rate between the two surfaces. All right. We are proceeding really exactly in the same way that we did for infinite parallel plates, with the difference that the shape factor in one direction is 1, F1 to 2 is 1, F2 to 1 is A1 upon A2. That is the only difference that we have in this case. Therefore, further, if I now write for E1, I write epsilon 1 sigma into T1 to the power of 4, and for E2 I write epsilon 2 sigma into T2 to the power of 4, then I will get Q1 to 2 is equal to sigma A1 T1 to the power 4 minus T2 to the power 4 divided by 1 by epsilon 1 plus A1 by A2 plus A1 upon A2 into 1 upon epsilon 2 minus 1. Now, only two surfaces are involved, it is only a two surface enclosure. So, obviously, Q12 is also Q1 and it is also minus Q2. All right, we have argued this before. So, it is the same argument again. If two surfaces are involved, the heat exchange rate between the two surfaces is also the rate at which heat is supplied as each of those surfaces. So, Q12 is equal to Q1 is equal to minus Q2. Therefore, Q1 and Q2, Q1 equal to minus Q2 is nothing but the expression which we have, that is namely sigma into A1 T1 to the power 4 minus T2 to the power 4 divided by divided by 1 upon epsilon 1 plus A1 upon A2 1 upon epsilon 2 minus 1. And this is a rather well known expression which I would like you to note. This particular expression that we have derived is a rather well known expression. As I will show you in a moment, it has wider applicability just for the situation for which we have derived it, and therefore, it is rather an important expression. Q1 equal to minus Q2 is equal to sigma A1 to T1 to the power 4 minus T2 to the power 4, the whole thing divided by 1 by epsilon 1 plus A1 upon A2 into 1 by epsilon 2 minus 1. Okay. Now, let us consider a different situation. Let us say, considering the annular space between two tubes, two long tubes, concentric tubes, let us say we consider the annular space between two concentric spheres, radius, the inner sphere being of radius R1 and the outer sphere being of radius R2. All right. Let us consider that situation. We have two concentric spheres and the inner sphere of surface 1 is at a temperature T1, the outer sphere, the hollow space of the outer sphere is at a temperature T2, the hollow surface I mean, and the heat exchange by radiation is taking place in the annular space between the two spheres. We want to find out the rate of that heat exchange. In this case, in the case of the two spheres, you will agree with me, f 1 to 2 is again 1, all right. F 1 to 2 is 1 and f 2 to 1 is a 1 upon a 2, where a 1 upon a 2 is nothing but r 1 squared upon r 2 squared. In the previous case, in the cylinder's case, a 1 upon a 2 was r 1 upon r 2, now a 1 upon a 2 will be r 1 squared by r 2 squared, all right. Now, if I proceed to derive an expression for the heat exchange between the two surfaces and derive an expression for q 1 or q 2, you will agree with me that since f 1 to 2 is 1 and f 2 to 1 is a 1 upon a 2, I am going to get exactly the same expression that we derived earlier. So, for the case of concentric spheres, if I want to derive an expression for the radiant heat exchange in the annular space between concentric spheres, the expression will still be, for concentric spheres also, the expression will still be q 1 equal to minus q 2 equal to sigma a 1 into T 1 to the power 4 minus T 2 to the power 4 divided by 1 by epsilon 1 plus a 1 by a 2 into 1 by epsilon 2 minus 1. So, this expression is also valid for calculating the radiant heat exchange in the annular space between two concentric spheres 1 and 2. Why? For that matter, why do the spheres have to be concentric, or why do the two cylindrical tubes have to be concentric? They could even be eccentric, because even when they are eccentric, f 1 to 2 is going to be 1 and f 2 to 1 is going to be a 1 upon a 2. You follow? So, even if the two tubes are eccentric or even if the two spheres are eccentric, the relation that we have derived is still valid. The only thing to remember is, if they are tubes, a 1 upon a 2 will be r 1 upon r 2. If they are spheres, a 1 upon a 2 will be r 1 squared upon r 2 squared. That is the only difference. All right. Now, let us go further. Let us carry the argument still further. Why do we in fact need to think only of cylinders and spheres? Suppose I have any general situation, a two surface enclosure with f 1 to 2 equal to 1 and f 2 to 1 equal to a 1 upon a 2. I have any general situation like this, could be 2 dimensional or it could be 3 dimensional. So long as I satisfy this condition, f 1 to 2 equal to 1 and f 2 to 1 equal to a 1 upon a 2, then the expression which we have derived is valid. Now, look at the examples like this. For instance, here is a semicircular tube, all right, a semicircular space, let us say. The semicircular part we will call as surface 2, the flat part we will call as surface 1, and let us say surface 1 is at a temperature T 1, the surface 2 is at a temperature T 2. This could be a long semicircular space like this, all right. Now, in this case, f 1 to 2 is 1, because all the radiation from the flat surface 1 has to go to 2, and f 2 to 1 is going to be a 1 upon a 2. Therefore, the expression we just derived is valid, all right. Let us go to this case. Here is a case where we have, let us say, two square or two rectangular tubes, long square or rectangular tubes, one inside the other. Here also a 1 f 1 to 2 is 1, f 2 to 1 is a 1 upon a 2, and the relation which we have derived earlier is true. This need not be 2 dimensional, it could be a 3 dimensional situation. For instance, a 1 could be a cube inside this room and a 2 could be the walls, the 6 walls of this room. You follow? That case also f 1 to 2 is 1, f 2 to 1 is equal to a 1 upon a 2, all right. So, for a variety of situations, although we derived this expression which I derived a moment ago for the annular space between two cylindrical tubes, although we derived it for that specific situation, keep in mind that this relation is valid whenever we have a 2 dimensional or a 3 dimensional situation involved in such a manner that f 1 to 2 is 1 and f 2 to 1 is a 1 upon a 2, all right. In that case, this expression holds true. So, this expression has very wide validity, and that is why I said it is a rather useful expression, and we will need it for solving many types of problems. Alright, so let us now in fact look at some problems. But before I do that, let me take a special case of this situation. So, we have got this expression now, q 1 is equal to sigma a 1 t 1 to the power 4 1 upon epsilon 1 plus a 1 by a 2 1 by epsilon 2 minus 1. This is our general expression, valid whenever f 1 to 2 is 1 and f 2 to 1 is a 1 upon a 2. Let us take a special case of this now. Let us say a 1, the area a 1, that is the surface 1, is very small compared to 2, that is a 1 by a 2 tends to 0. In that case, the denominator will simplify, because a 1 by a 2 will become equal to 0. So, the expression will simplify to the form q 1 is equal to sigma epsilon 1 a 1 t 1 to the power 4 minus t 2 to the power 4. So, we will get this simpler expression if a 1 by a 2 tends to 0. Keep that in mind. So, now we have derived a general expression for a variety of geometries, though we started off only with the case of the annular space between two tubes. We extended it to the annular space between two spheres. We said the spheres could be eccentric, the tubes could be eccentric, and then we said in fact it could be applied to any situation where one object completely surrounds another. So, that one surface completely surrounds another. So, that f 1 to 2 is 1 and f 2 to 1 is a 1 upon a 2. And then finally, we took up this special case and said if a 1 by a 2 tends to 0, we get this simpler expression. Now, we are going to solve a problem or two. The problem we are going to take up first is the following one, which occurs in practice quite often. Let us say I have a furnace on the left hand side here. We would like to calculate through a small opening in this furnace, this is an opening in the furnace, what is the heat being lost by radiation through that small opening. So, out here the shaded thing is the wall of a furnace, on the left hand side is the furnace like this, all right, and it is at a temperature of 1000 degrees centigrade. There is a small opening and we would like to know how much heat is being lost by radiation through this small opening in this furnace wall. Let us say all the surrounding surfaces to outside the furnace are at a temperature of 300 Kelvin and the furnace wall itself on the outside is at 300 Kelvin. All right. Let us say that the furnace wall is at 300 Kelvin here, and of course, all the surroundings are at 300 Kelvin. And this is my opening through which radiation is being, heat is being lost by radiation. I would like to know how much is being lost, because inside here the temperature is 1273 Kelvin, that is 1000 degrees centigrade. So, furnace inside here at 1000 degrees centigrade. So, how much energy, radiant energy is being lost through this opening? Now, we are going to solve the problem as follows. We are going to idealize the situation by making a two surface enclosure. So, we are going to say close this opening with this dotted line that I am showing here, close this opening with this dotted line which I am showing here, all right, and close this opening with some imaginary surface, and let us call that as surface 1, all right. And let us say all the others, that is the outside of the furnace wall, that is here, and the surroundings, everything else is at 300 Kelvin. So, let us call that as surface 2. So, let us say this is my enclosure as I am showing it here, this is my enclosure in which the opening is surface 1, the small opening is surface 1, and everything else that it sees once the radiation comes out is surface 2. So, obviously, this is a situation in which a 1 upon a 2 is going to be tending to 0. It is a situation in which f 1 to 2 is going to be 1. It is a situation in which f 2 to 1 is going to be a 1 upon a 2. Therefore, for this particular problem, for this particular problem, which we have idealized as follows. For this problem, we can say Q1 is equal to the expression which I just showed you a moment ago, sigma A1 epsilon 1 T1 to the power 4 minus T2 to the power 4. That is the rate at which heat must be supplied at the surface 1. If surface 1 is to be at 1000 degree centigrade, that is 1273 Kelvin, and surface 2 is to be at 300 Kelvin. All right. So, that is equal to 5.670 into 10 to the minus 8, that is the Stefan-Boltzmann constant, multiplied by the opening. We are told to take the opening to be 2 centimeters in diameter. I will put that down. Opening (2 centimeter) diameter. All right. So, A1 will be pi into 0.01 the whole squared, pi r squared, that is the area, multiplied by the emissivity of the surface, that is we can treat it to be a black surface. So, we will say it is 1, and T1 to the power 4 would be 1273 to the power 4 minus 300 to the power 4. Okay. So, we imagine that the opening is plugged with an imaginary surface, all right, and that imaginary surface is at 1273 Kelvin and is a black surface. Now, that is a good assumption, because the opening inside is really looks like a black surface from outside. So, that is a good assumption. So, we get 1273 to the power 4 minus 300 to the power 4, and that comes out to be equal to 46.6 watts. So, in this case, this is the rate at which heat is being lost by radiation from this opening in a furnace wall. All right. Now, let us do one more problem. The problem we want to do next is the following. Now, I am going to read it out slowly so that you can take it down. The problem is the following. A thin metal spherical container of diameter 32 centimeters is filled completely with liquid nitrogen. I repeat, a thin metal spherical container diameter 32 centimeters is filled completely with liquid nitrogen. Full stop. The container is surrounded by a thin metal concentric spherical shell of diameter 36 centimeters, and the space between the two spheres is evacuated. And the space between the two spheres is evacuated. The surfaces of the spheres facing each other are silvered. And have an emissivity of 0.02. I repeat, the surfaces of the spheres facing each other are silvered and have epsilon of 0.02. taking the latent heat of vaporization, of liquid nitrogen to be 201 kilojoules per kilogram and the density to be 800 kilograms per meter cubed. Find the rate at which nitrogen evaporates. Let me repeat that sentence. Taking the latent heat of vaporization of liquid nitrogen to be 201 kilojoules per kilogram and the density to be 800 kilograms per meter cubed, find the rate at which nitrogen evaporates. Assume that the ambient temperature is 303 Kelvin and that the liquid nitrogen is at 77 Kelvin. I repeat the last sentence. Assume that the ambient temperature is 303 Kelvin and that the liquid nitrogen is at 77 Kelvin. Okay. Now, let us picture this situation. I want you to focus only on the left hand side of this figure for the moment, not on the right hand side, so that you see the geometry involved. The inner circle is the spherical container of diameter 32 centimeters. All right, surrounded by another spherical shell of diameter 36 centimeters, and there is a neck here through which the liquid nitrogen is poured or taken out. This is all filled with liquid nitrogen. All right. So, cryogenic liquids like liquid nitrogen are stored in spherical containers. The sphere has the advantage of providing the smallest area for a given volume, and so it is advantageous to have a spherical shape. You want to, after all, reduce the amount of heat flowing in, which will make the liquid nitrogen evaporate. You are told the ambient air is at 303 and the liquid nitrogen inside is at 77 K. All right. Now, let me, the rectangle that is drawn here, it is expanded and let us magnified, and let us look at the magnified view here, so that you see the whole picture now. What you are seeing now is the inner shell, and this is the thickness of the metallic shell, and the zigzag line indicates that it is silvered. Similarly, this is the outer shell, this is the thickness, and the zigzag line indicates that it is silvered. The space between the two is a vacuum. Okay. So, this is the inner shell, this is the outer shell, the space between the two is a vacuum, and the two surfaces facing each other are silvered and have an emissivity of 0.02. Okay. Now, when heat flows, it will flow from outside to inside. Obviously, the outside temperature is 303 Kelvin, the inside temperature is 77 Kelvin. So, heat is going to flow from outside to inside. Okay. Now, when it flows, I think it is obvious to you that it will encounter a large number of thermal resistances. And what are these? There are 5 thermal resistances in the path of the heat flow from outside to inside. What are they? There are 5 thermal resistances in the path of the heat flow from outside to inside. What are these? Number 1, convective resistance on the outer surface of the outer shell, on the outer surface of outer shell. That is the first resistance. Then heat flows by conduction through the outer shell. So, resistance to heat flow by conduction through outer shell. That is the second resistance. Third, resistance associated with radiant heat flux, radiant heat flow the radiant heat flow across the annulus, across the vacuum annulus. That is the third resistance. Then the fourth is again resistance to heat flow by conduction, resistance to heat flow by conduction through inner shell. And the last resistance will be the convective resistance, on the inner surface of the inner shell. All right, these are the 5 thermal resistances. Now, out of these, the dominant resistance in this case is going to be the resistance associated with radiant flow across the annulus, number 3. That is going to be the dominant resistance. That is the purpose of having that vessel in which you are storing the liquid nitrogen. You have a vacuum between in the annular space, you silver those surfaces. So, you try to reduce the radiant heat flow rate, that is your dominant resistance. Therefore, what we are going to do is, we are going to say this is so dominant a resistance that the other resistances are insignificant. So, although I have a situation like this, all right, across the annular space, starting from the outside, a resistance here, a resistance by conduction here, then the radiant heat flow dominant resistance, then a resistance by conduction here, then a convective resistance. I say the dominant resistance is in this vacuum, and therefore, I can assume that the temperature, if it is the dominant resistance, I can take this temperature to be 303 and this other temperature at the inner surface to be 77 Kelvin. All right, I will say since it is the dominant resistance, all the temperature drop really takes place across this dominant resistance, and therefore, take the temperature of the outer surface of the inner shell to be 77 and the temperature of the inner surface of the outer shell to be 303. If I do that, then it is just a substitution into the expression we have derived. We will get Q1 is equal to, now I am substituting sigma A1 T1 to the power 4 minus T2 to the power 4, the whole thing divided by 1 by epsilon 1 plus A1 upon A2, 1 by epsilon 2 minus 1. Just substitute into this expression now. All the data is given. So, if you substitute, you will get 5.67. Let me just show that now. substituting, you will get 5.67 into 10 to the minus 8 to 4 pi into 0.16 squared, that is A1, 77 to the power 4 minus 303 to the power 4 divided by 1 upon 0.02 plus 16 by 18 the whole square, that is A1 upon A2, 1 upon 0.02 minus 1, which is minus 1.73 watts. And if I want the evaporation rate, I find out how much evaporates during the whole day and divide by the latent heat, and I get 0.74 kilograms per day. All right. Now, I want you on your own to show that the resistances which we ignored, that is the convective resistances and the two convective resistances and the two conductive resistances, are in fact insignificant. We have studied conduction, you know the values of H that you would get in convection, you should be able to show that in fact they are insignificant and that the temperature drops across those would be insignificant compared to the temperature drop that we encounter in the annular space. Now, we have come to the end of what we wanted to do in radiation. Let me just sum up the some of the topics that we have covered in radiation. We have covered first basic concepts, then we have covered emission characteristics of surfaces, then we have covered the laws of black body radiation, then we have talked about radiation incident on a surface, what happens to it, it is absorbed, it is reflected, etc., and defined terms like absorptivity, reflectivity, etc. Then we have talked about the directional nature of radiation and defined terms like solid angle and intensity of radiation. Having done all this, we then derived expressions for heat exchange by radiation between black surfaces. Heat exchange by radiation between black surfaces. In the process, defined an important term called the shape factor, then went on to radiant heat exchange in an enclosure, with black surfaces, and finally we talked about radiant heat exchange in the annular space between between two tubes, two spheres, etc. And we took the special case finally today of A1 upon A2. The last thing which we looked at was the special case when A1 upon A2 tends to 0. Now, we have come to the end of what we wanted to do with radiation, and we will now be turning our attention to the third mode, convection, studying first a little fluid mechanics and then studying convection.